In this video, we're going to start learning how we can manipulate an equilibrium to do what we want it to do. So we've talked about how all reactions will proceed until they reach equilibrium, and then they will stay there forever as long as you don't mess with them. Today, we're essentially talking about how you mess with them. Usually, as a chemist, our goal is to create as much product as possible in most scenarios. For instance, if you're working for a pharmaceutical company trying to create some new drug, you want to maximize your yield because that is going to minimize your cost, and companies like that. Even in an academic setting, if you need to do research on a particular compound, you want to create as much of it as you can, as cheaply as you can. You have a limited budget. So we're going to be applying something known as the Chatelier's principle that allows us to strategically shift an equilibrium in one direction or the other by applying this concept. So what the Chatelier's principle tells us is when a system at equilibrium is subjected to a stress, the system will shift in a way that relieves the stress and reestablishes equilibrium. Essentially, what this amounts to is for certain types of stresses, which we'll talk about in this video and the next, what those are, whatever you do to an equilibrium system, it will try to undo. So if you add extra of one reactant, it will shift to get rid of that. If you take reactant away, it will shift to put it back. Whatever you do, the reaction is going to try to undo by shifting in whichever direction, forward or reverse, accomplishes that. So what kinds of things count as stress? So what can stress out a chemical reaction? So there are two main things that we're going to talk about, one in this video and the second in the next. They are changes in concentrations and changes in temperature. So these things change either Q or K. And when we're talking about Le Chatelier's principle, we're always starting with a system that's already at equilibrium. You can apply the same ideas of Le Chatelier's principle when you're not starting from equilibrium, but for the purposes of this course, for the purposes of keeping things relatively simple, when we're talking about these types of stresses, we're going to be starting from the system at equilibrium, where Q is equal to K, and then when we apply one of these stresses, Q is not equal to K anymore. And we know how things will shift depending on whether Q is less than K or greater than K. So first up is changes in concentrations. So changing concentrations changes the value of Q. So remember that Q is the value of the equilibrium expression at any point in our reaction. And it is essentially products over reactants raised to the power of their stoichiometric coefficients. So products over reactants is really the thing to keep in mind here when you're thinking about how Q is going to change and how that's going to affect the reaction. So there are different types of changes. We can add or remove reactants or products, and those will affect the value of Q in different ways and therefore affect the equilibrium in different ways. So if we add reactant or remove product. So adding reactant would be making our denominator larger. Removing product would be making our numerator smaller. Both of those things end up decreasing the value of Q. If we start at a place where Q and K are equal, and we suddenly make Q smaller by either adding reactant or removing product, that means that Q is now less than K. After we have applied that change, whenever Q is less than K, our reaction proceeds in the forward direction. So our reaction needs to go forward to get back to equilibrium. So no matter what you do, your system is going to try to get back to equilibrium however it can, whichever way it needs to shift in order to do that. So whenever you either add a reactant or remove a product, you can expect to see that your reaction is going to go in the forward direction or produce more product in order to get back to equilibrium. So adding additional reactant is one of the most common ways that chemists force a higher yield than a reaction may want to do otherwise. It is really, really common in chemical synthesis that you have one complicated reactant. Complicated also means expensive generally, and you're often reacting that one complicated reactant with one really simple reactant. You often build things up kind of piece by piece like Legos. So what chemists will often do is use a really, really high concentration of the cheap reactant to try and force the equilibrium as far towards the product side as possible, thereby maximizing their percent yield. If you want to go in the other direction for whatever reason, you could either remove or decrease the concentration of reactant, or add or increase the concentration of product. Now we're doing the opposite. We're making our denominator smaller or our numerator bigger, both of which increase the value of Q. If we were starting out at equilibrium and we just increase the value of Q, Q is now greater than K. And whenever that is true, our reaction needs to run in reverse to get back to equilibrium. So next you're going to see a short demonstration of this type of process where I'm adding reactant and adding product to shift a reaction back and forth using a pH indicator known as bromothymol blue, which is yellow in acidic solution and blue in basic solution. And you'll see that shifting back and forth as I add reactant and product. So in this cylinder here, I have a sample of bromothymol blue in distilled water. So this is a pH indicator, which means that it changes colors in the presence of acids and bases. So I have a simplified version of the reaction that's going on here. Essentially, we have two different forms of the bromothymol blue. One of them has an extra hydrogen atom attached, and they just happen to be different colors. So the one on the left with the extra H is yellow, the one on the right without it is blue. So as we add acid and base, we can shift this reaction and watch it react. So right now, we have mostly the yellow form since our solution appears yellow in color. So if I add some base into this, I'm going to expect to see my system react by shifting to the right. And in this case, that means that we're consuming yellow stuff and producing blue stuff. So if I add some sodium hydroxide, which is a base, we will see that happen. So my system started out at equilibrium. Nothing was changing, it was a constant yellow color, so it was at equilibrium to begin with. I disrupted the equilibrium by adding some base, and it reacted, since the base appears on the left side of our equation, it reacted by trying to get back to equilibrium, which means consuming what we added. So it shifts away from the yellow side towards the blue, because that is going to use up both of these things, using up the thing we added to produce more of the products. I can push this back in the other direction by adding acid. So I have some HCl, which is an acid. When I add acid, that appears on the right side of our equation. Our system will react by shifting back in the other direction to consume the product that we're adding. So at this point, our system is once again at equilibrium. We can see a constant color. So our equilibrium looks visually different, but this still is at equilibrium because nothing is changing. When I add my acid, my equilibrium will be disrupted. And we can see now that it is reacting, trying to get back to equilibrium. And once again, equilibrium has been reestablished once things stop changing. So the only time we are not at equilibrium is during that shift, is during that color change. And once things settle down and stop changing again, we are back to equilibrium. And I can keep shifting this back and forth as much as I want. I can disrupt the equilibrium and eventually it will reestablish. That was adding base. I can add acid. So we can see that this is reversible. I can go back and forth and back and forth. And whatever I do to my system, it tries to undo by shifting the reaction either left or right to, in this case, take away whatever I have added. So we can apply these same ideas to any reversible reaction. So here we have zinc hydroxide reacting with H+ to form water and zinc ions. So we can consider each of these potential changes and determine which direction our reaction is going to shift by assessing what happens to Q, what happens to K, to determine which is larger. So since we are only changing concentrations here, we are not changing K. The equilibrium constant remains constant if all that's changing is the concentrations, but we are affecting the value of Q, which means that after each of these stresses, we may have a situation where Q is greater than K or Q is less than K, which will dictate whether our reaction shifts forward or reverse, respectively. So the first thing you're going to want to do is write your equilibrium expression, and that's going to help you determine how these different changes actually impact the value of Q. So why don't you take a few minutes and try to write the equilibrium expression, determine if Q increases, decreases, or stays the same, and then what that means about how the reaction will shift, forward, reverse, or not move to get back to equilibrium. So the first thing we want to do is write our equilibrium expression. It'll help us figure out what's going on. So if we look, we've got a liquid here and a solid here. Those are going to get ignored. But on the product side, we have zinc ions, which are aqueous with a coefficient of 1, exponent of 1. And then on the reactant side, we have hydrogen ions, coefficient of 2, so that gets an exponent of 2. So this will help us see, as our concentrations change, how Q will change. So our first stress here is increasing the concentration of H+. So if we're increasing this concentration, we're increasing the value of our denominator, makes the fraction as a whole smaller. So adding additional product is decreasing the value of Q, which means that Q is now less than K. They started out at equilibrium, always the assumption we're making here. We decrease the value of Q. Q is now less than K, which means our reaction needs to run in the forward direction to get back to equilibrium. We've added extra reactant, so our system wants to get rid of that reactant by running in the forward direction, which uses up reactants to produce products. For the second one, we are adding more zinc hydroxide solid. So this one's a bit tricky because if we think about what affects Q, the only things that affect the value of Q are the things that actually appear in the equilibrium expression. So adding additional solid zinc hydroxide is not going to change anything. So in this case, we haven't actually stressed our system. Q is still equal to K. It's the concentrations that matter, so just adding more of that solid isn't changing the concentration of anything that actually appears in our expression. So this is not going anywhere. It is still at equilibrium. You haven't actually disrupted it at all. Then, last but not least, we have the addition of zinc nitrate. So this one is also a little bit tricky because at first glance, you see there is no zinc nitrate here. How is this related? But what you have to remember is that this is aqueous. When this is dissolved, our ions exist separated. That whenever an ionic compound dissolves, the ions dissociate, the ions separate in solution, which means that what we actually have are zinc ions and nitrate ions as separate things. The zinc is present in my reaction and is present in my equilibrium expression. So the addition of zinc nitrate is adding zinc. The nitrate isn't going to do anything. It's just going to be a spectator. That won't affect anything. But the addition of zinc is increasing this concentration, making my numerator larger, increasing the value of Q, which means that Q is now greater than K. So we have stressed our system, we have taken it away from equilibrium, and to get back, my reaction needs to run in reverse.